All right. So now we're moving on to rotation. And we've already explored rotation a little bit when we did polar coordinates and circular motion, but that was being viewed in the context of Newton's laws of motion. Now we're kind of moving on from momentum, which again, you can think of momentum as this kind of alternative way of how you view dynamics, where rather than focusing on the specific interactions that occur at a point of contact, which allows you to then apply Newton's laws, we saw that there were more global ways that we can analyze motion in terms of this thing called momentum. That sometimes is conserved, sometimes it's not, depending on your system, but it is something that seems to be able to flow between objects in your system or in and out of the system. Unlike forces, which are things that kind of just magically instantaneously appear at points of contact, and then if that contact is lost, they vanish. There's no conservation or distribution of force. That doesn't really make sense. So if we pull this in now with rotational motion, another kind of momentum pops out, angular momentum, that allows us to kind of re-envision how we can do dynamics. So rotation we've seen before, where some of the conventions are that, there's conventions that counterclockwise motion is taken as the positive direction. So if you're thinking of a 2D coordinate system, counterclockwise is positive, clockwise is negative. And we've already talked about, or we can pull back from introphysics, this idea that we can use vectors still to describe rotational motion. You can, of course, always use vectors to describe, say, the position, the velocity, the acceleration of a point particle. But if that particle is moving in a circle, is there a way to encapsulate, perhaps as a vector, that rotational motion? Particularly how it's rotating. Is it rotating like this, or is it rotating like this, or rotating like this? And then is it rotating like this, or is it rotating faster or slower? Or is it rotating the opposite direction? So we can define kind of an angular velocity. Not kind of define, we can define an angular velocity, omega, which we will treat as a vector, that specifies speed and direction of rotation. Speed and direction of rotation. So you could imagine, for example, a spinning disk that is spinning kind of in this sort of way, into and out of the page, perhaps. And again, if there was a particle on that disk, I could describe, if I wanted to, if I say put my ordinate at the center, I could describe the position of a particular particle on that ring, and it would move as time went on, and we could specify that there is some overall motion going on with that particle. And you might be able to infer then how it's rotating and how fast it's rotating. This rotation vector is something that we will specify that points along the rotation axis. So if I think of this dashed line kind of going through the center of the ring, we'll say that's the AOR, or the axis of rotation. That everything is spinning around. And so we'll make omega be a vector that points in the axis of rotation. And the magnitude of that vector then specifies the angular velocity, where the units of the magnitude of omega we then expect to be something like radians per second. Or we might write that as theta dot as well. That's another way we've seen this appear, right? It's specifying the amount of radians that are being traversed every second by an object. The directionality is done by the right-hand rule. So if I put my thumb and pointing along the direction of omega, my fingers then curl in the direction of rotation that disk is undergoing. Similarly, if I had another disk that was rotating in the opposite direction, the vector I would specify for omega might look something like this, in which case if my thumb points along omega, then my fingers curl in the direction of rotation. So this is an example of a vector expression that is containing information about rotation. And then we can also have angular acceleration. Often alpha is used, which is the time derivative of this vector. This would then specify radians per second is the thing speeding up, slowing down, or maybe is the axis of rotation changing possibly. Since again, accelerations tell you how velocities change, so we just now add the word angular in front of everything. Angular accelerations tell you how angular velocities change, which then specifies how the axis of rotation might change. We'll come back to that. This has the additional slightly added challenge that while the angular velocity is a vector, the angular acceleration is a vector, angular position is not. I can write, say, the position as, some of the kind of Cartesian coordinates, x, y, and z. I cannot necessarily define kind of an angular motion, which you might think of as a rotation. Right? You cannot really say that some general rotation that an object undergoes can be written as, say, angle x in the x direction, angle y in the y direction, etc. And the reason why it doesn't have a vector nature is that rotation is not commutative. Like vectors must be. Remember, what does commutative mean? That means the vector a plus b then is equal to the vector b plus a. That is not the case. So maybe I'll put, right, this is not the case for rotation. And I could give an example. Let me find a textbook that we'll use. Where's our actual textbook? We'll use the actual textbook. You might be able to say, like, could I define a rotation of this general book as I first rotate it 90 degrees in the z, around the vertical axis, and then I rotate it 90 degrees around the x-axis, which I'll take to be pointing towards the screen. So if I have the book that initially is like this, and I rotate it kind of 90 degrees in this direction, that starts here. You're looking at the spine. It goes this way. I've rotated about this axis, right, the z-axis. And now I'm going to rotate it 90 degrees about this axis. So then I might get something that ultimately looks like this at the end of the day. So you went from something that was here, rotating in z, rotating in x. And you get this answer. Now let's do the same two rotations, but in the opposite order. So first I'm going to rotate it around the x-axis here. So it goes from this to this. And then I rotate it around the z-axis. So it goes from this to this. And at the end of the day, you end up looking at the back of the book, which is different than if you first did z then x compared to x then z. So rotation is not commutative. So you cannot describe kind of angular motions, or angular positions rather, in this kind of vector sense. That won't be too bad in terms of how we're going to ultimately be able to do all of this, since, again, forces tied to accelerations or how velocities change. So we're going to be all right, I think, at the end. Before we get into the idea of momentums, we could ask, what is the connection between v and omega in general? If I have, say, a spinning top maybe I'll even use a spinning top as my example. If I have a spinning top, here's my spinning top, and it's spinning on the table such that it has some omega vector that points upward through the middle of the top, above this kind of point at the bottom. And I want to describe, say, the position, let me use a different color, maybe this point right here on the top, and after it rotates a little bit, it finds itself maybe on this, this part of the top, so it's rotated a little bit in this case. Can I say something about the velocity of that point? And again, I want to then ultimately focus in on the calculus limit where I zoom in and it's not 2 points wildly different in theta, but kind of from here, a little, and it rotates a tiny bit. Well, I got to specify this relative to some sort of coordinate system. So maybe I'll specify the origin kind of at the point where the top is, hitting the ground. This ultimately doesn't matter where I put my origin. This is going to be a general result, but let me put it there for right now, because I think then it's easier to visualize. Then in this case, the position vector is initially going from the origin to that point, then final position vector goes something like that. And while this origin is helpful for us to get this, again, general result, the useful thing to notice here is that the angle between the position vector and the rotation vector, let's call that phi. In that case, it's always a constant, right? As it sweeps out, right, the angle that this pen is making with the vertical is always the same angle as it spins around. So there's a constant angle there. The angle between phi the angle phi is the angle between the position vector and omega. If we look at this with a top-down view, right, in this case, the point might start here at the top, that might be our initial, and then it might end up here at our final. So this is kind of top-down, where omega is kind of pointing out of the page through the dead center. Then it looks like what's going on is, right, there's, looking at it from the center, which the origin is somewhere below into the page, on the center. This is kind of the initial position. This is the final position. And it has swept out some angle d theta in terms of how much rotation it's occurred. So if it rotates by delta theta, there is a connection between all of these variables. And then if we think of this in the calculus limit, we'll be able to get an answer. Where in this case, now it's kind of busy here, so let me get rid of that. In this case, in going from here to here, that is the magnitude of the change in position, right, delta r, in that case. How the position has changed, ultimately it's gone from that initial point to that final point. And this angle here is then delta theta. Now it actually isn't too hard then, right? I have a triangle. It's not necessarily a right triangle. It's a general triangle, but there is a connection between the sides of the triangle, the two black lines, which are both equal in length, and then this delta r. So let me just jump to the answer. So this change in the position vector, the magnitude of it actually, ends up being 2 times the magnitude of the position vector times the sine of that phi angle. So essentially you're projecting the position vector onto this kind of top-down plane. And then there is a sine of delta theta over 2. That corresponds to the amount that the rotation has occurred. And that's the change in position ultimately that's going on. Now what I want to do is I want delta theta to get smaller and smaller and smaller, so I can think of this in the calculus limit, and then maybe connect delta r, which sounds like it's close to a velocity. If I divide by time, that'll give me a velocity. Maybe then I can say something more general. So then let's do this in the calculus limit. So then this becomes kind of dr on the left-hand side. You got 2, you got r, that hasn't changed and it doesn't get small. Sine of phi doesn't get small. But then you got sine of d phi over 2. So you got the sine of a tiny, 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 tiny angle. Remember from Taylor series that the sine of something tiny is just equal to, is well approximated by just that tiny thing. So then this is approximately just d theta over 2. The 2's cancel, and then notice you get dr is the magnitude of r times sine of phi multiplied by d theta. Now I'm going to divide by dt. And that looks like it dr by dt equals the magnitude of r. I have d theta by dt, and then I have the sine of the angle phi. To help me connect this with vectors, I'm going to realize that the d theta by dt, well, that's just theta dot. That's the magnitude of omega in this case, multiplied by the sine of phi, which happens to be the angle between r and omega. Look at the first 3D image for justification on that. So the magnitude of two vectors multiplied by the sine of the angle between them, that sounds like a cross product. And indeed, you can then convince yourself that in general, the connection between the vector velocity, the linear velocity, is omega cross the position vector. This gets you both the magnitude, which again is what we just kind of argued. The magnitude of the left side, which is the velocity, is the magnitude of position times omega and the sine of the angle between them, which itself is a cross product. This also gets the directionality correct. You know, if I look at r omega in this image above right here, oops, that was supposed to be a highlight, and right there. At this point in time where it's drawn, it's kind of coming out of the page. And we could ask ourselves, does the cross product give me the right direction for a velocity pointing out of the page? Well, cross product, I first have my fingers pointing along omega. Which way can I curl them so that they point towards r without having to break my knuckles? Right, it's this way versus this way. So I can do it that way, and then my thumb points out of the page at that particular location. So this is good, a good thing to remember as a connection between linear velocity and angular velocity. This is a general result. You don't have to have your origin at kind of the bottom of the top like we did above, but I think that makes it clear how this thing comes about. All right, so with that, let's define angular momentum. And what we're going to do is, if you think here about how velocity is kind of relating an angular velocity, or the linear velocity is being related to kind of angular motion that depends on how you're looking relative to some position, right? Notice that r appears in that equation above. Let's define angular velocity as the cross product r with the regular momentum. Essentially trying to turn a linear thing into an angular thing. Now, things to notice with this angular momentum. It also doesn't have a special unit, right? So in this case, it looks like angular momentum is, again, if I think of position or momentum as mass times velocity, it looks like it's r cross v. So the units of angular momentum looks like it's kilograms times meters per second, or kilogram meter squared per second. We don't give it a special unit when we're talking about angular momentum. And it also, notice, depends on r. You need to be able to specify the position in order for me to say something about the value of angular momentum. But to specify the position means that you have established a coordinate system such that there is an origin that you have chosen. So the value of L depends on your coordinate system. This is unlike regular momentum, P. P is just mass times velocity. That is independent of any coordinate system you throw down. But since position specifically enters into angular momentum, this then requires you to specify a coordinate system first, and then specify that this is the angular momentum relative to that coordinate system. So that's a little different than regular momentum. Also, by the nature of the cross product, this angular momentum vector is perpendicular to the position at a given point. The angular momentum vector is also perpendicular to the velocity, or the momentum more generally, at a given point. Now, why this definition will become more clear in the next couple of videos, where when you are thinking about rotational motion, this definition does end up creating something that is very analogous to regular momentum. You might think it would have been nice if momentum is mass times velocity. It would have been nice if maybe we could have written down angular momentum as some sort of rotational mass times some sort of rotational velocity. And you will see in cases, particularly extended systems, you can do that, but we call it rotational inertia and then angular velocity. But this is, again, something that we could write down regardless of whether or not the motion is actually rotational motion at all. Right, let's take an example, a pretty simple example. Suppose I have a particle that starts at some position x naught, y naught, and just moves to the right with some constant velocity. I can measure the angular momentum of this particle, and I'm going to measure it relative to some origin that I must specify. So given how I've written it down, I'm going to measure the angular momentum from this particular origin. Again, you have to specify it for angular momentum. So then that's kind of the initial position, and then at some time later, right, we might imagine that the final position is going to be something that just moves horizontally to the right. And if it's moving at constant velocity, it looks like this is x naught plus v naught t, and then it's always at y naught. That is kind of the general, at a given point in time, that's the position. So the angular momentum, and again, let's take this particle to have mass m. Looks like this is m r cross v. I know how to take cross products, right? There's m, and then the cross product is this determinant thing. R looks like it's x naught plus v naught t, y naught 0, and then v naught is v naught 0, 0. And most of these things are zeros, except it looks like the only one that lives at the end of the day ends up being minus y naught, v naught, and it's in the z direction. Essentially, this part of the determinant that lives, and everything else touches a 0 at some point. So it's negative, so I would say that corresponds to into the page. And the fact it's negative actually is giving you a sense, if you want to really think of this in terms of rotation, which again, this is not rotational motion, but if you want to think of it in terms of rotational motion, this negative angular momentum does suggest, let me just redraw it down here. Right, let's take an initial position, let's say right here. In this initial position, I might say, if I really wanted to view it in terms of rotation, it has some initial angle theta naught. And then as it moves horizontally, it eventually has some final position here, where the final angle, if I wanted to measure the angle relative to the x-axis, has shrunk in this case. So this is, if you want to think of this in terms of rotation, this is, in a sense, clockwise motion, in that, if you imagine if something was rotating clockwise, the angle would be shrinking, as it approaches the x-axis. In this case, it's not rotating per se, but the motion is causing the angle towards the x-axis to shrink, like it does in clockwise motion. So again, since clockwise is negative, the angular momentum in this case is negative. Take the alternative example of, let's have motion that is purely vertical. So maybe it starts here at r naught and then moves up here at some final r naught. Now let's do the same thing. In this case, r at some arbitrary time t, it looks like it's always going to be x naught, y naught plus v naught t, and then no z directional motion. V is then 0, v naught, 0. For mass m, you can figure this out. Do the cross product. I get m x naught, v naught in the z direction. Particularly positive m x naught, v naught in the z direction. So it's positive. That suggests it's pointing out of the page. And again, if you think of this in terms of angles, it initially has some angle here, theta naught. But then as it moves to have some larger angle, theta final. So it's as if the motion is kind of counterclockwise in that case. Theta increases as you move counterclockwise. Since we take that to be the positive direction, the angular momentum as a result is positive. Right, so we can write counterclockwise motion. And just to make it clear how much this depends on your origin, I could take the same exact problem of purely vertical motion, but maybe I shift my coordinate system such that the origin is immediately below it. Right, so essentially I could think of taking the origin and moving it over a little bit, and then I measure angular momentum from this location. Well, in this case, position is 0, comma, y naught plus v naught t, comma 0, and then v is the same, unchanged. And I'll let you convince yourself that when you take the cross product of these two, you get 0 as a result. Given that you could also just immediately see this, right? Again, think conceptually. Both of these only have a y component, no x component, no z component. So that means they are either both parallel or they are anti-parallel, depending on the signs of all those coordinates or variables rather. Right, so I know that r and v are parallel or anti-parallel, and I know the cross product vanishes when they're parallel or anti-parallel. So I expect the angular momentum to be 0 in that case. Again, same motion, but what you say is the angular momentum depends on where you've placed your origin. So is there a best place to put your axis of rotation? No. Of course, there are some that will make your life easier in terms of the mathematics. So I would say, in general, put your axis of rotation, or put your origin rather, somewhere along the axis of rotation. That's going to make ultimately the math a lot simpler. But again, you could do it from whatever rotation axis, or whatever origin you want. And things do definitely get tricky, especially, imagine a car wheel it's not attached to a car and is just rolling down the road. Well, there is the case where if the wheel is kind of always constantly moving in the same direction, right? Imagine it's going like this. By the right-hand rule, the value of the angular velocity would be kind of where my pencil is pointing. And if it's kind of always moving in a straight line, the axis, right, that also gives you a sense of the axis of rotation, and it's always going to be constant and pointing the same direction, even though it's kind of translating. Compared to, say, a wobbly tire, where not only is it moving towards the screen, but its axis of rotation might also be changing as well. That is more complex rotational motion. We are going to, for now, stick with instances, rigid objects, etc., that have a fixed axis of rotation, or an axis of rotation that is only moving via translational motion that's perpendicular to it, right? So like a car, kind of always moving in one direction versus it wobbling around. All right, so that is an assumption we're going to make. We're going to stick with kind of rigid objects with fixed axes of rotation. Maybe also allowing kind of translations perpendicular to omega. Okay, also. Because again, I want to try to zoom in on particular kinds of rotation that we can study, because I don't want to get too complex, because the most general version of this there's whole chapters dedicated to this in the second half of your textbook. And it can get pretty messy. But I still want to establish some relationships between angular momentum and regular momentum. Or analogies, rather. So let's start with angular momentum and ask, how does angular momentum change? Momentum changes when forces are applied over time. Let's look at the time derivative of angular momentum for a point particle. So then the mass is just a constant. And I know the derivative distributes, so this looks like it's then going to be r dot cross v plus m r cross v dot. Where r dot, of course, is just v, right, to use RVA instead. So this looks like it's v cross v plus, and then it's r cross a at the end of the day, if I don't want to use dot notation instead. Well, a vector dotted with itself, we of course know that the cross product vanishes in that case. And this looks like at the end of the day, it's m r cross a at the end of the day. Or if I move the m back in, r cross the mass of that particle and its overall acceleration of this particle, which of course then is what? Well, that's just, by Newton's second law, the net force acting on that particle. So how does angular momentum change? It's this quantity of the position vector crossed with the net force on the object. This we define to be what we call torque. Tau of it is position cross F. Or I guess in this case it would be the net torque. In general, I can define a torque for a particular force as r cross that particular force. So in that case, what does this say at the end of the day? Then how does angular momentum change with time? It changes by a torque being applied to an object, which is Newton's second law for rotational motion. If forces change momentum over time, then torques change angular momentum over time. And again, the analogy in this case is very, very clear. Right? How does momentum change with time? Well, we said that's a force, such that we could write change in momentums is force over time. Similarly, how does angular momentum change over time? Well, we said that's this thing called torque. So how does angular momentum change? Well, that's torque multiplied by time. So in this case, they are directly the same in terms of how we can think of this as just vectors, right? I could, I've been calling these things momentum, angular momentum, and force torques, but I could just as much call them Bob and Frank and Mary. And there'd be no difference between the two lines that, on the top and the bottom. Think momentum. If this is the initial momentum, and there's a force that's applied over time, right, that's to the right, then at some time later, the final momentum is going to be pointing a little bit towards the right. And we can think of that, momentum's easy to visualize, right? It's moving initially straight up, but then the motion of the car or whatever is then moving a little bit to the right. If I think of angular momentum pointing straight up, which again, you might imagine this has something to do with rotation. And we haven't really made a direct connection between L and omega yet. But for these rigid objects, we're going to be with fixed axes of rotation. It turns out that the angular momentum and omega are often going to be parallel to one another. So we can think of the angular momentum as giving us something about the rotation that's going on. Not that the object is moving straight up, but that's where I put my thumb, and then it's rotating around that arrow. Then if a torque is applied over time, the angular momentum then at the end of the day ends up pointing a little bit more to the right. Which again, easier to visualize with regular momentum. I'm moving up, there's a force pushing on it, so eventually I start moving in this direction instead. Angular momentum pointing up, so you can think of the rotation kind of looking like this, but then a torque is applied, which makes not the object start moving in this direction, but maybe it starts rotating more like this. So rather than going in and out in this direction, it's kind of going in and out in this direction as a result. So there is kind of a rotation going on with the axis of rotation in that case. Torques can change angular momentum, both in magnitude and direction, right? If they're parallel, changes magnitude. If they're perpendicular, only changes direction. If it's some combination, like it is for the two that I've just drawn, it can do both. So then the last thing I'll say for today is, can we take the analogy even further? Can I say something then about the conservation of angular momentum? Does it similarly hold that maybe if regular momentum is conserved when there's no net external force, is it the case that angular momentum is conserved when there's no net external torque? So let's ask ourselves. So let's define the L of the system as, in just the same way, the sums of all the angular momentums of all the individual angular momentums of the particles within the system. And then ask ourselves, what is the derivative of this? And do we then get something that looks like, say, net external torque instead? So the proof, jumping to the end, yes, we do. But it's a little bit subtler. So again, let's assume a fixed origin All right, so we're measuring angular momentum from some origin. Let's assume it's a fixed origin. That's one kind of condition that it has to hold. And I won't prove, but I'll say how this generalizes at the end. Then let's think about that time derivative. So big L dot then looks like it's going to be the time derivative of this big old sum of individual momentums, or the time derivative of a sum of the individual masses times the positions crossed with the velocities of all those particles. Let's see. Maybe actually I don't even need to do it in terms of velocities. Let me write this instead as, let me stick with momentum. And this is just R cross the momentum. Positions and momentums of individual particles, summing over I. Well, I know the derivative distributes over sums. So this looks like it's then going to become V cross P sub I plus the sum of R cross the time derivative of momentum. That first term, P is parallel to V, so V is parallel to momentum, and so that means the cross product then vanishes. So that entire thing is 0. In the second case, what is the time derivative of a particle's momentum? Well, that's the net force acting on the particle. So it looks like in this case then, this ultimately becomes the sum of the positions crossed with the net force acting on that particular particle. So the sum of a bunch of positions crossed with forces, which does look like a torque. Now, similarly to what we did with regular momentum, where remember with regular momentum, we took that net force and we broke it up into two parts. One part of all the forces that were external to the system, and then one part that was all the kind of inter-system interactions going on within the system. So I'm going to ultimately then write this as, this is there's two sums here. There's position crossed with kind of the net external force acting on I, plus a sum of all the positions crossed with all those all those internal interaction forces, on I from J, where this is summing over J not equal to I. And again, you can go back to the momentum lecture, right? Because again, this is a very analogous proof. So we got the net external force. I'm dropping net just so my subscript isn't too big. That's the first kind of big sum term. The second term is kind of a nested loop, or a nested sum rather, of all the interactions going on with inter-system forces. Now, before we were able to argue that in that sum of forces, there was always Newton third law pairs. And of course, there still are always Newton third law pairs in that sum. But we have to be careful now, because since the cross product involves the position, it is not the case that, across different particles, I will always find, where there's Fi on J, there will always be then Fj on I. Now I have to ask, somewhere in that big nested sum on the right, there is a term that looks like R sub I cross F on I on J. And the Newton third law pair comes in, but then that's the position of R sub J cross the force of J on I. And while the forces have negative sign, are related by a negative sign, those two positions might be very different. Maybe this is worth just drawing a quick picture, right? If this is R sub I, and this is R sub J, right? Those are very different positions. And somewhere in this big messy thing on the right, there's a term that looks like r sub I cross f of I on I from j. But then there also is a term somewhere where it's r sub j cross f of j on j from I. And if it was just the two forces, they're related by a negative sign, they add up to 0. But now, since that cross product involves a position, those two positions are very different. But Newton's third law will still come to the rescue, because I will use Newton's third law to write this as I on j with a negative sign. And now, since I know the cross product distributes, I'm gonna try to combine these two terms and write these two terms as instead I minus rj, that's some vector cross force of on I from j. Right, so those two terms that have the Newton third law pair added together, those are the same thing as r of I minus r of j, whatever that position is, which actually we know what that is. When you have the difference of two vectors, what's the rule? To the first one from the last one. So that seems like this is some vector here. This is ri minus rj. And then whatever that force is, that interaction force between them. And again, if I would love to be able to say this is equal to 0, because if I say this is equal to 0, then that means, just like we had with regular momentum, all those Newton third law terms will end up canceling each other out. Now the thankful thing is that I can say this is equal to 0. Under a particular assumption, which this one is just, I have to take this as a given, but at least scientific experiments seem to support this approach. Equals 0. Now you could think, what's other ways that cross products can be 0? We've used it a couple times already. If the two vectors are parallel or anti-parallel to one another, then the cross product is 0. And we are going to claim that that is the case here, that r sub I minus r sub j is parallel or anti-parallel to the force between them. And this is on the assumption that interactions, when they occur, are forces that point towards each other. So this is assuming the forces between two objects point towards one another. Right, I push my hands together. There are two forces. In this case, they're kind of pointing towards one another in equal and opposite directions. I take two objects that are being attracted with each other gravitationally. Those forces are pointing towards one another in equal and opposite directions. In these instances, the forces are pointing in the same direction, either parallel or anti-parallel, to the vector that is drawn between them. In this case, r sub I minus r sub j. In that case, the force then is parallel or anti-parallel to that difference vector, and this cross product vanishes. So at the end of the day, the total angular momentum changes by what's left over, just the sum over I of the positions crossed with the net kind of external forces that are acting on I. That is how the angular momentum of a system changes. So we might call that sum on the right the net external torque. Since torque is a position crossed with a force, right, that looks like it's the sum of a bunch of torques. So then external torque changes the angular momentum of the system. And so if there's no net external torque, the derivative angular momentum is 0, or that says the angular momentum vector is some constant vector, which of course is just a statement on the conservation of angular momentum. Now, notice while the analogy was pretty strong between regular momentum and angular momentum, there were some additional conditions that we had to make. If the origin which you were measuring angular momentum from was allowed to also move, this gets trickier. Right, so the conditions we had is that the origin was fixed, and of course that the frame was inertial, so that these were true forces, not fictitious forces. Turns out everything I just said also works in another common situation as well, which if the origin is moving but is placed at the system's center of mass, this also holds. Kind of the common example I can think of, so let me write that down. Also true if the origin is located at the system center of mass. Which might be moving. And again, kind of the example I have is, if you have a wheel rolling down a ramp, and you want to study the system of the wheel, in which case the wheel has lots and lots of particles in it. And I maybe want to do it from, make my life easy, right? I'm going to have my origin be located at the axis of rotation of the wheel, which is in the center. These sorts of results still also hold in that case as well, where the origin is moving, but it's following the center of mass of this system. But again, it does get tricky. Ideally, you can put your origin somewhere where it's stationary. And then if you're in an inertial frame, you can say that the net external torque, again, as is measured by that coordinate system you've laid down, you will get different answers depending on where you put your origin. But again, you are free to choose your origin to be wherever you want if you can pick one such that these sorts of conservation properties pop out or allow you to use them. That often can then be very, very helpful to you. All right.